Hello everyone. In this video, I'll be discussing few examples of solution to Poisson's and Laplace equations. Let us start with the Poisson's equations, which is del square V equals to minus rho V by epsilon, where rho V is the volume charge density of the region and epsilon is the dielectric constant of the medium or the region which we are considering. And V is the potential which is going to be found by solving this Poisson's equation. Take the example of p-n junction. In the p-n junction, let us consider the orientation is through the length of x-axis. This side, left side is the p-type material and the right side is the n-type material. We know in this p-n junction, near to the junction, there will be concentration of immobile charged particles. So the charge density, volume charge density throughout this p-n material, if we know, then we can find what is the potential distribution of this region. And in turn, we can also estimate the electric field distribution of this p-n junction material. So for the charge concentration, we already know near the junction, there will be immobile charge carriers present. So the charge concentration near the p-n junction is high. So at the junction, it is less, and near the junction, the value of concentration of charged particles in the p-type material and the n-type material is more. And towards the x direction, the charge concentration reduces. So we have considered the origin or the center at the junction. Towards the right, the x-axis is positive, and towards the left, the negative x-axis is considered. That you can see from this. Suppose if we know the charge concentration, that is the volume charge density of this junction, then we can estimate what is the junction potential. That is one application of solving this Poisson's equation. And we are not going to solve this. I'm just giving the examples, and you can refer the textbook and understand what is the solution they have given. Here, I'm just giving an overview of what examples can be taken for solving the solution of Poisson's and Laplace equation. Now here, this is a one-dimensional potential function. It talks about one-dimensional potential function because the axis here taken is x-axis and the potential will be varying as a function of this x. The distance will decide the potential distribution. Here in this case, x is the axis we have taken and potential will be a function of only this one dimension, which is x. So this kind of examples talks about one-dimensional potential function. So p-n junction and the junction potential is estimate of solving the Poisson's equation. This is one example. Like this, many examples in the electrostatic field problems are there, which takes the Poisson's equations to find the potential function. In most of the junction capacitances, we can estimate. Here in the p-n junction, if we estimate the potential function, then we can estimate the junction capacitance effect also. In case of transistors, mostly in FETs, this potential distribution at the junction and the capacitance effect at the junction will be estimated by taking this Poisson's equation. Next, let us talk about Laplace equation. Laplace equation is a special case of Poisson's equation where if the region is charge-free, then the equation will simplify to Laplace equation, which was discussed in the earlier videos. You can refer those videos for how we have derived the Poisson's and Laplace equation. Now, for the case of charge-free region, the equation reduces to the Laplace equation, which is del square V equals to 0. Means this region, here in this case, this region has charge concentration, but in some examples where if the region has no charges between the two potential variation, then we can make use of this Laplace equation, solve this to get the potential function. In turn, we can estimate the capacitance effect between the two different potential regions. So we can have one-dimensional potential function in all the three coordinate systems. We know rectangular system has three variables x, y, z, and cylindrical system has three variables rho, phi, z. Spherical system has three variables r, theta, and phi. Suppose if we consider one-dimensional potential function in rectangular system, b can be taken as a function of x or function of y or function of z. And in cylindrical system, b can be taken as a function of rho or phi or z. And b can be taken as a function of only r, only theta, and only phi. So these are the functions of only x, only y, only z, only rho, only phi, only z. And we are going to consider some specific examples for these one-dimensional potential function. Suppose if I consider v as a function of x or y or z, the only difference is the axis orientation of the axis. So if I consider potential variation as a function of x or y or z, the example will be same, but only the orientation of axis is different. So when we consider these cases can be put together for the example of parallel plate capacitor. If we consider two parallel plates of capacitor is placed perpendicular to x-axis, then between these two plates, potential is a function of x. Or if I consider this axis as y, then potential will be a function of y. If I consider this axis as z, then the potential will be a function of z. We know in case of parallel plate capacitor, these two are two conducting plates which are parallelly oriented. And between these two plates, we have an insulating material. We call the insulators as dielectrics, whose dielectric constant is given as epsilon r value. Now, if we estimate the potential difference, then we can find capacitance as charge concentration. So capacitance can be obtained as the amount of charge stored. Suppose if I connect this to positive potential and if I connect the second plate to negative potential, then the first plate will be charged to plus Q and equal negative charge will be distributed on the second plate. Now, if I consider the capacitance, capacitance is defined as the ratio of charge stored in either of the plates divided by difference in potential between the two plates. So how much of difference in potential is there between the two plates and the charge concentration decides this capacitance value. This capacitance has to be estimated from this Laplace equation. How we can solve this? By taking this Laplace equation, del square V equals to 0, we will solve this equation to find what is the potential. After knowing the potential function, we can find the electric field intensity, which is negative gradient of potential. After knowing this electric field intensity, we can find the electric flux density, which is epsilon times E vector. And charge concentration can be estimated as surface integration d dot ds. This is from the Gauss law. Now, if we know the charge concentration, then ratio of charge concentration divided by difference in potential gives the capacitance. So this is how we will be solving for finding the capacitance, or potential can be estimated first from the Laplace equation. Then whatever is required, we can estimate from the known values. This is an example of one-dimensional potential function of x or y or z. So these four cases brings together an example which is the parallel plate capacitor. Similarly, we can look at the cases of other one-dimensional potential functions in all the three coordinate systems. The second one we can consider is potential as a function of radius of cylinder. If I consider two coaxial cylindrical plates, or when we consider this is the axis of the cylinder, one cylinder of smaller radius, another cylinder of larger radius having the same axis contributes this capacitive effect for the coaxial cylindrical plates. Now, between the inner cylinder and outer cylinder, if we have the dielectric material with dielectric constant epsilon r, there will be capacitive effect between the two plates, inner plate and outer plate. Thereby, we can estimate the potential from solving this Laplace equation. Since the inner one and outer one are differing with radius rho, we can estimate this difference in the potential as a function of rho. So this is another one-dimensional potential function which is having the variable rho only. Now we can make use of this Laplace equation and find this one-dimensional potential function for rho. And similarly, we can estimate the capacitance of this cylindrical capacitor. But one thing you should know, this is a second order differential equation. Del square V equals to 0 talks about second order differential equation. To solve for the second order differential equation, we need to have two boundary conditions. So the two boundary conditions is required to solve for getting the constants of the differential values, and the integration of this will give the potential function V. those constants can be estimated by applying the two boundary conditions. We need to have two boundary conditions to solve for this Laplace equation. When I take the each case of example like parallel plate capacitor or cylindrical capacitor, that time we will know how to solve for this in having the boundary conditions. Now, this is the second example which talks about the cylindrical capacitor, where potential is a function of radius rho of the cylinder. This is the case 2. Now, we can consider the next one in spherical system, where the example case is the concentric spherical capacitor. Case 3 talks about two spherical plates which has the same center. So we call this as the concentric spherical plates, and the effect of capacitance produced by this is called the concentric spherical capacitance value. The inner one is of a smaller spherical radius and the outer one is of the larger spherical radius. Between these two, we have the dielectric material with dielectric constant epsilon r. Since the inner one and outer one are differing in radius, between the two plates, the potential function will be a function of the radius of the sphere. So V of R gives the example for solving concentric spherical capacitor. That is this case 3 where V as a function of R, only R. And when we talk about the fourth case that we are going to talk is V as a function of phi, angle phi. We know angle phi is the azimuth angle. The azimuth angle will be taken. If I take the reference XYZ axis, the azimuth angle will be taken from X axis and it goes around in the entire 360 degrees or 0 to 2 pi radians. Now, if I consider the variation of this azimuth angle in both cylindrical system or spherical system, the azimuth angle is the same variable, which is the rotation of angle from X axis towards the entire 360 degrees. If we consider two radial planes at two different angles, suppose this is at specific angle of phi as 0, another one is at a specific angle of phi as 45 degree. Now, between these two plates, potential function exists, which is a function of angle phi. And one more important thing to note is these two plates should not touch each other. We know conducting plates have equal potential. If these two plates touch each other, then there will not be any difference in potential. For a single conducting plate, potential is same. Conducting plates have equipotential values. So if these two plates are at least separated by an infinitely small gap, then we can estimate the difference in potential and the potential function between the two plates as V as a function of phi. If these two are touching each other, both will be at same potential, then there is no potential variation between the two plates. So we have to maintain a small, infinitely small gap between the two radial planes to estimate V as a function of phi in this case. This is case 4, which is the capacitance between two radial planes, and the medium between the two planes is having the dielectric constant epsilon r. And the last case will be potential function of theta. So we know theta is the elevation angle, which is from the positive z-axis. This is the variation of angle theta. Now, when we consider two conical conducting plates or two conducting cones, one is at an angle of theta 1, another is at an angle of theta 2. Between these two conducting cones, if the material is having the dielectric constant epsilon r, then between these two cones, the potential function will be a variation of only angle theta. And here also you should know the two conducting cones should not be touching each other, because if they touch each other, potential difference won't exist between the two plates. Potential will be same. So if we maintain an infinitely small gap between the cones, then one will be at a potential V1, another will be at a potential V2. So there will be a difference in potential, and the function of V of theta will be existing between the two conducting cones. So these are one-dimensional potential functions where parallel plate capacitor can be taken as an example as V as a function of only X, or V as a function of only Y, or V as a function of only Z. This depends on what axis we are considering perpendicular to the parallel plates. If I consider this axis is X, then V as a function of X should be taken. If this axis is considered Y, then V as a function of Y should be taken. And if this axis is considered as Z, we should consider V as a function of Z. Then for cylindrical capacitor, where the axis is same, then the potential function between the two cylinders is a function of only variable rho. For concentric spherical capacitor, between the two concentric spheres, the potential function will be varying only with respect to the variable r. And between the two radial planes along the azimuth angle phi, the potential between the two plates will be a function of only angle phi. And between the two conducting cones with two different angles, and the difference in potential between the two cones will be a function of only variable theta. So these are the 5 cases of one-dimensional potential function solution for Laplace equation. We'll be doing one by one derivation of finding the capacitance of all these 5 cases in the further videos. Hope you have understood the examples of solution to Poisson's and Laplace equations. Thanks for watching the video.